All right, happy Friday, happy V-Day. Thanks for joining me in our last lecture before reading week. It's the end of week 6, can you believe? Oh my goodness. Okay, we are going to finish the randomized algorithms and independence today. We have a few things to clean up. Okay, one is this example. Okay, so we did the parallel components example and used that as a means of scaling up a coin flip to as robust an algorithm as we want. This is sort of the opposite. So if you had a serial sort of circuit, if you will, and there are a whole bunch of components, a whole bunch of gates, if you will, that are switches that fail with probability p independently of each other, any one of them, of course, will break it because there's not going to be any path from A to B. So the other one, all the paths had to be broken in order for the thing to be broken. Here, any one of them, or several, but at least one would be broken to break it. Okay, so what's the probability the machine breaks? Okay, this is a way less robust way of building a machine. Of course, we would like, if we're going to build a machine like this, and many systems are built like this, right? There's a sequence of events, a sequence of pieces of code, if you will, and all of them have to function correctly all in a row for the whole thing to work, right? You need a very low probability p, or you'd like a low probability of any component breaking, so this would be a very small p. Anyway, similar to what we did before, we're going to label each event of breaking as for its component E1 for component 1, E2 for component 2, and we are going to try to find the probability that either E1 or E2 break. Okay, before it was E1 and E2 break, right? Here we have E1 or E2. Okay, we can rewrite this as the probability of E1 plus the probability of E2. And each one has a probability of P of failing, so this is P plus P, which is 2P. Okay, now this is a very common solution for this, but it's not right. Why isn't it right? What's wrong with this map? Yeah, so there could be overlap, right? There is an event where both of these things occur. And in fact, if you just sort of look at the probability P, I mean, if P is really big, I know I just said that it's probably really small, but if P is really big, you might get a probability here that's greater than 1, and that's probably not what you want either. Okay, so the math probably fails. Now, the reason that this has worked incorrectly is because the rule that we used here is, like the disjoint sum rule, applies to mutual exclusion. Okay? We're living in a land of independence, not mutual exclusion, and again, it's very easy to confuse these two things. Okay, so in the parallel one example, it was E1 and E2, E1 intersect E2. We could use exclusion to multiply them together. Independence multiply them together. If we have exclusion, we would have that this is not the same thing as mutual exclusion. Okay, so just as a reminder, independence is not the same thing as mutual exclusion. If you get independence, you get that A intersect B, its probability is the product of its bits. Okay, it's two probabilities, and mutual exclusion, the probability of A intersect B is 0. Okay, and those are two very different things. Okay, so the two things are not the same. So no, independence is not the same as mutual exclusion. If you had mutual exclusion, you could have equality here. The best you can do, I mean, you can use inclusion exclusion, which we'll do in just a sec, but the best you can do is use the disjoint sum rule, okay, and basically say it's less than or equal to 2p. That's perfectly valid, okay, but you can't have equality here. Okay, so I'll take the suggestion and use inclusion exclusion. So instead, use inclusion exclusion, okay, which will subtract off the probability of E1 and E2. Okay, and that one we can use independence on. I'm not going to write a specific extra line for that because I'm running out of room, but we would get P plus P, same as above, minus P times P. Okay, so this would be 2P minus P squared. And I don't intend to prove it here, but you can never get a number bigger than 1 by this quantity. Okay, so you can show that its maximum is 1. Now, one point I just want to make about this number before we go to the part B of this is that, P is going to be really small, like something very tiny to fail. Like even if it's 1%, 1% here, give us a 2% chance of failure minus something that's 1% squared. It's actually a very small number compared to these two, and oftentimes we will just approximate it away. It's almost like using the union bound in a way, right? Up here, it ends up being pretty much equivalent. Anyway, K independent components. How would you solve this? What if there are K independent components? What's the chance of failure? Oh, recursively do the union thing. I mean, so you're saying like we have the probability of, this thing, right? And then we have K, oh dear. Okay, that's the second bloop I've heard today, and in the spirit of love and all that, I don't want to get mad on Valentine's Day, but please make sure things are on silent. Yeah, so you could do inclusion exclusion on this, but it'll get really big in general, right? It won't get big? Yeah. It'll immediately simplify, but oh, I see. Yeah. I mean, you could do that. I think the algebra will get a little bit messy somehow, unless you had a good inductive hypothesis, but there's an easier way. You can try that and give it a whirl and show it to me. Maybe I just don't see it. Um, how could you do this? Yeah. No. Yeah. So some sort of suggestion, inclusion, exclusion for multiple sets. No, we're not going to do that either. Yeah. Good. You could do complement. The nice thing about doing complement is that these unions turn into intersects, and we can do something with intersects, right? Okay, so if we take the complement, it's going to be 1 minus the probability of the union of this thing, and I'll try to get maybe I'll get a thicker blue here so it's really clear. Okay, so you're taking complement of all that, and the complement of this thing will give you an intersect, right? Because it's De Morgan's law. Okay, so these components are independent. So you might ask yourself, what's the chances of it not breaking? It's 1 minus p times 1 minus p. All these things have got to not fail, right? So 1 minus p times 1 minus p times 1 minus p, all the way down. That's basically what's in there, okay? But just written out longhand so that it's clear that we're using independence. It's 1 minus p to the k. Okay, which has a very similar characteristic. It has sort of like the complement characteristic to the parallel machine, right? Except we're looking at what's the chances of success. We end up getting this product, this power in there. Okay, one last thing to note before we leave this problem is this quantity here. Okay, this quantity here you can approximate. You can do it in a couple different ways. You can you can look up a good approximation for this, and it's 1 minus k times p. But if you didn't know that, you could actually do the e to the minus p thing. Okay, so you can use that. E to the x is basically close to 1 plus x. And then you'd have e to the minus p to the power of k, so that would give you e to the minus p times k, and then translate it back to 1 minus pk. Okay, so this thing is actually very close to 1 minus pk or k times p, and that is similar to what's up here, right? This 2 times p, minus some other junk that's kind of small, all right? So if you sub this back in, you would get it's equal to about k times p, okay, when p is small. Okay, I'm going to show you the Freevolt's algorithm today, and yeah, before I get into that, I've had a very lonely week. I feel like I can open up to you because it's Valentine's Day. I've had a very lonely week. I had 3 office hours this week, and 0 people showed up. Normally I get 1 or 2, and that's kind of a bad day. But I had a really bad week. I guess 0. 0 is a very special number. And I asked my TAs this week. I sort of checked in on them, and they had very small numbers as well. Something like on the order of about 5 customers all week, and that's a pretty low number for 15 office hours. Of course, it's up to you whether you choose to use our office hour time. And if you had no problem with this assignment, then by all means, don't use our time. But this is a very small amount of office hours used compared to assignments 1 and 2. Maybe assignments 1 and 2 were tough, or maybe I don't know, the internet was able to help you a lot more with assignment 3 than the other 2 assignments. Okay. If you feel like I'm speaking directly to you, then I'm concerned that you're doing things the wrong way. It might not impact your grade on assignment 3 because maybe we might not notice that you copied, say. But this is critical work. This is critical work for things like your midterm test and the material that goes beyond. Okay, so just be very careful for what's going on going forward. I am concerned about the number of hours, and if it's some other reason, it's some other reason. But if it's the reason that I'm thinking of, please be careful. We did this problem last time, which was a hard problem. Yeah, do you have a question? Okay. This is like 1 minus p is like e to the minus p. This is like e to the minus pk, and this is like this. Okay, so if you don't know anything about like how polynomials approximate, you can just use the e to the p thing. Okay. All right, 5 dice. This was a hard problem. Okay, I admit it was a hard problem, and it became much simpler by breaking it down into cases, 6 cases. Somebody asked me at the end of class a very astute question last time as well. What happens if you have fewer dice, or sorry, if you wanted to divide by a different number, say, or your dice had, like you want to divide by 5 or divide by 7. This wouldn't work. It wouldn't be as clean. That's the bottom line. But the technique is still good, and you could do an approximation for that thing anyway. Okay, even if the number wasn't exact. And we're going to see an example of that by using this exact same technique. We start with the law of total probability, and then we try a whole bunch of cases. Okay, so if it's divisible by b, or if it starts off with a total of 4, then we end up with 6 different cases. Only one of them is divisible by 6. The technique we're going to use it for is not for 6 different ways. It's going to be 2 different ways. Okay, it's either going to be true in one case or true in the other case. Right? So it's only going to be 2 things that we're conditioning on for a total probability, but we're going to do something similar that will allow us to take a common factor. It won't be a 6th this time, it'll be a half, and then plug this partition back in. Okay, so we're going to do the exact same thing as last time, but to, matrix multiplication is 0 or a 1. These are the 2 cases we're going to do, a coin flip instead of a 6-way die. Okay, so let's start here. Everybody had to do some sort of linear algebra to get into this course, so hopefully this is a review. Okay, you had to learn about matrix multiplication. But in case you forgot, you can multiply 2 n by n or whatever by whatever matrices, as long as the number of rows in B equals the number of columns in A. You can multiply them. And the way that you generate C is by taking all the rows of B and hitting all the rows of A. And when I say hitting, I mean you take the dot product. Okay, so the dot product means that you take the first elements of first of the row and the first of the column, the second of the row, and multiply them thirds and fourths and all the way down, and then you add them all up. And this is a fairly computationally intensive operation. It requires n multiplications in the n by n case. Okay, so multiply all those things, and then you add them all up, which requires 1 fewer addition because you add them in pairs, right? Okay, and that's just to generate one entry, to generate Cij, and of course I and j can roam between 1 and n and 1 and n. Okay, so you end up with n squared entries, each one costs you n. Okay, so by the miracle of multiplication, the big O stuff, you end up paying big O of n cubed. Okay, matrix multiplication is expensive, but it has lots of applications to math problems, so maybe it's a good idea to try and optimize this. This has been attempted by many computer scientists. The first one of note is Strawson. Strawson used the divide and conquer method to get this thing down to partitioning the matrix into 4 quadrants, 4 equal quadrants, and doing submultiplications. And by being clever, he only had to do 7 subcases out of the 8. So this number up top here is a strange exponent, I know, for an algorithm, but this is actually log base 2 of 7. And the reason that it's log base 2 of 7 is, there's some math behind this for the master method. When you take compute 307, you'll see this exact formula used in 7 subcases, and you're dividing them into cases that are half the size. So that's sort of where this generalization comes from. These other algorithms have improved upon this in slight ways. This Coppersmith-Winograd algorithm is a refinement of Strawson, where they subdivide in a cleverer way, and they refine it down to 2.376. Okay, so the exponent gets smaller. Almond Williams had the gold star until I failed to look this up while proofreading this. There is a paper from 2024. Nice, where they actually got it down to big O of n to the 2.371. This is by Williams, of the same Williams that I put a stroke through, and 3 co-authors, Zhu and Zhou. Okay, so this is from 2024. The problem with these algorithms is that the leading constants, and you have to remember big O has a leading constant that we sort of ignore, it's very large. And you only start benefiting for n's that are like massively huge. Okay, so the practical cases, maybe it's not as good as just doing something straight up like n cubed. Anyway, the theoreticians believe that you can get it down to something as close to n squared as you would like, but they haven't done that yet. Anyway, that's a little bit of background. The goal of today is to verify matrix multiplication. And so we're going to set you up with this scenario, and the scenario is, suppose that you have a friend, because you would never do this to a real friend, right? But suppose one of your friends, maybe a classmate, says that they implemented one of these algorithms, like maybe the current world record holder, which is pretty complex, probably difficult to implement correctly. Okay, but anyway, they produced the output C, and you wanted to verify that C was actually correct for some large A and B. Okay, so because you're their friend, you want to do this. How would you do it? Okay, so this is maybe one of the obvious things to do is to just multiply things yourself. Okay, and to do that, if you don't know anything about the algorithms themselves, maybe you just do the obvious order n cubed thing, which might cost you a lot of time, but it's a fairly simple algorithm to implement. Or you could do something more clever, like the order n to the 2371, which is the new world record holder, if you're really trying hard to save some time. Or you could do something probabilistic. Okay, so you could use sampling and another Monte Carlo technique to verify that the two things are equal in order n squared steps. And this is a technique called Freevolt's algorithm. And the idea is as follows. It's similar to the primality testing, is that you take a random input, it's basically a vector, a 0, 1 vector, and you multiply C, and you multiply it by AB. And then you get the result, and if they happen to be equal, then, life is good. And if they happen not to be equal, then, you say no. Okay, so the error is on, I think the other side this time, all right? So you say, well, I guess it's no to primality. Yeah. So this is no, it's not correct. So it's the same side if these things don't agree. Otherwise, you try again, and again, and again, and again, and again, until you're satisfied. Okay, and as long as each one of those tests ends up being a coin flip, you can do the same scaling up that we did before. Okay, so this is the approach, and we're going to actually prove that this thing, if you pick a random bit vector, you'll have at least a probability of a half of it saying no when it's correct. Okay, so I'm just going to show you the basic step. Okay, so the single test and the scaling up is the exact same scaling up that we saw from before. K parallel components. All of them have to fail for it to fail. Okay, it's the same idea. Okay, so this basic step is a repeatable, independent test. Okay, so here's the technique. We generate a random bit vector. This is Colleen Bernoulli coin flip n times. Okay, so this takes order n steps. Okay, pretty simple. We compute each of these things. We compute t is b times x, and then we sub this t back in and multiply it by a, and then we do the same thing for c. Okay, if you look at what it takes to multiply, and the first step here is this is b, right, and it's n by n, and then you multiply this thing by bit vector, which is n by 1. Okay, so for each of these rows is hit by that one column, right? So you do n, n, n. Okay, so you do it for each of those n items. Okay, and you do n amount of work, so that's going to be order n squared for this, and there are 3 of them, right? So it's going to be order n squared, order 3n squared, but we throw away the 3, of course. Okay, and this technique is good because it'll save us from multiplying a and b together as a pre-processing step, right? If we did that, we would pay order n cubed, so we want to avoid doing that. Okay, so just 3 of these multiplications. And we compare y and z. Okay, so y is the result of multiplying ab times x, and z is the multiplication of c times x. Okay, so we just check to make sure all the entries are equal. That's order n checks. So the total running time, we add all this up, it's dominated by n squared. Okay, so a basic step costs you n squared. And of course, we're going to run k basic steps. It's going to cost us kn squared, and still n squared. Okay, first thing to note, if AB is equal to C, so your friend did the multiplication correctly, then it's going to always report yes, Y is equal to Z, okay, in every case, unless you did something wrong, but you didn't, right? But the converse isn't necessarily true. It might be that you got unlucky in the cases where they're not the same. Okay, so if the algorithm reports no, it's definitely true. It's not. They're not equal. But if it's yes, it might still be unequal. Okay, we use the same terminology here. If we ever find an X for which they're not equal, then X is a witness, and we immediately say no. Right? So we're saying, if they're not equal, how many times are we going to get yes all in a row? Well, it's going to be 1 over 2 to the k, basically. Is it going to lie to us with such a small probability? Well, maybe. Okay, so let's see how this thing works on an actual test case. Okay, so suppose A is equal to this and B is equal to this. If you multiply those 2 things together, it's actually not this. Okay, so the actual A times B is, let's just quickly do this. So this is 1, 1, so that's a 1, 1, 0 is a 1, 1, and 0. Okay, so these 2 things are, this is not C. Okay, so the A times B is not equal to C. Okay, so what might happen here, let's give it a try, is casing. We generate a random bit vector, say it's 1, 0, we multiply z out. Okay, so this is c times x. It looks like this. And let's just hit this vector here. So that's 1 times 1 and 1 times 0 is 1. And this gives us a 0. So that's 1, 0. Okay, this one here. Okay, so when we multiply this out, okay, so we do it in stages. Okay, so we evaluate this bit first. Okay, so we'll save this A matrix for a moment later. Okay, so this bit first, that gives us a 1 and a 1. Okay, so that's t. And then you multiply this one out, and that's 1, 1. And that's good, right? These two things are not equal. So it would report no, which is what we want. Okay, so yay, that's good. Okay. In another case, if it had generated 1, 1, okay, as our random bit vector, we multiply that by z, we get 2 on the top and 1 on the bottom. Okay, so that's the resulting z. And here when we generate t, okay, so this is, let's just repeat the A here, future step. So this is 1, 2. Okay, so again, that's our t. And then we do the matrix multiplication for this bit, and it gives us a, did I do this wrong? No, what is that? 1, 2. Oh yeah, that's right. That's right, we want this thing to say they're equal, yeah. So this is equal. Okay, so when you generate the bit vector above, it correctly says the matrix C is incorrect. Okay, so it says no, and down here, if you started with 1, 1, it incorrectly output yes, even though AB is not equal to C. Okay, I'm going to pause here before we move into the proof. Okay, we have enough probability stuff available to us to prove that the probability that it's going to give us an incorrect yes is less than or equal to a half, okay, which is sort of our goal. Okay, are there any questions about how the basic step is operating? Is it clear? Yeah? Okay, first thing we're going to point out, or I guess we're going to define, is E, the error matrix. Okay, we're not actually defining this because, we're defining it, we're not calculating this thing because we're not actually calculating A times B. Okay, but mathematically, we can define this thing. And R is the product of E times X. Now, if we just quickly look at what E times X is, E times X is, let's see, so let's just check what's going on here. E times X, E is C minus AB times X, and you can use the distribution law on this. It's C minus AB times X. Okay, and these are the things that we defined, or we calculated as part of the basic step, right? So Cx is Z, and ABX is Y. Okay, so R is the residue. The reason we call it the residue is because, if the multiplication was done correctly, the residue is going to be 0. And why? Because E will be 0 if the multiplication was correct. Okay, so that means that we're always going to get a yes. So R is equal to 0. That means that R is equal to Z minus Y, Z is equal to Y, which means that this algorithm always gives you yes. Okay, so if you've done the multiplication correctly, it's always, always yes. Okay, and that's not very interesting. Okay, we want to see what happens when E is non-zero. What's the chance of it giving a yes? Okay, well, if E is non-zero, then there's got to be at least one entry that's not 0. And it's going to be somewhere. It's going to be on row I in column J. To make the notation a little bit easier so I don't have to write a whole bunch of I's and J's, we're going to assume that it's on row I. It actually doesn't affect anything, but it's easier for me to write a 1 than it is an I, and it's less confusing for you. Okay, so we're going to assume that it's on row 1. Okay, so we ask the question, what's the probability that R is equal to 0? First thing we're going to say is that the probability, okay, so the probability the algorithm says yes equals the probability that the R is equal to 0. This is less than or equal to half. So proof, what's the probability that R is equal to 0? Well, it's got to be the probability that R1 is equal to 0, and and R2 is equal to 0, and R3 is equal to 0, and Rn is equal to 0. And that's a lot of zeros. But we're only going to focus on R1 because we know that there's a non-zero entry on row 1. And this is a lot of extra conditions we don't need. Okay, so we're going to use monotonicity and say that this is bounded above by the probability that R1 is equal to 0. Okay, so we're going to look at R1. We're going to say, what's the chances that R1 is 0 by accident, by fluke? It's less than or equal to a half. Okay, that's what we're going to show. Okay, how do we do it? First, what is R1 equal to? R1 is equal to the product of x with, I guess, e. So this is going to be e11 times x1 plus e12 times x2 plus e1n times xn. Which is n things. Now, the thing that I'm interested in is the term that has e1j in it. Okay, so e1j is the non-zero entry. Okay, so this is equal to e1j times xj plus a sum of a whole bunch of other stuff. So it'll be e1, I don't know, k times xk. And this is for all, k not equal to j. Sorry, I'm going to change my mind writing the j there first. So this is k not equal to j. Okay, so we know, okay, so just a reminder where we are here. So this thing here is non-zero. Okay? That's the only thing we really know about what's in the error matrix, is that that thing is non-zero. We don't know what to say about any of the other things. Okay, one last simplification we're going to do, and then we get to do the probability stuff. Okay. So this is equal to, same thing here, e1j xj plus w, where w is the sum of this other stuff. It's not that we don't care about it, it's just we don't need all of its complexity going forward. W is some number that's generated by this. Okay, and I want to move up the page here. Okay. So R1 is equal to this. And we know that E1j is non-zero. All right, the stage is set. Now, here's where the 5 dice thing comes in. All right, we don't know what's in W, but we know that it's either 0 or non-zero. And we're going to do 2 cases. Either it's 0 or non-zero. And what about the law of total probability? The probability that R1 is equal to 0 equals the probability that R1 equals 0, given that W is equal to 0 times the probability that W is equal to 0, plus the probability that R1 equals 0 given that W is non-zero times the probability that W is not 0. And I'll give you a moment to catch up. Okay, this is the trick from before, and it's interesting because I have no idea what this quantity would be for a random bit vector, right? Like, what's the probability it's 0? What's the probability it's non-zero? These are really hard things to quantify, right? Really, really tough. Okay, but we don't have to know. Okay, and we'll see why in a second. The reason is we can figure out what these are, and they're each going to be a half. Okay, so did I spoil it? I didn't really. All right. Okay, let's just do a little aside here, and let's look at R1. Okay, so R1 is E1j xj plus W. We are going to look at the probability that R1 is equal to 0 given that W is equal to 0. Okay, well, let's sub these numbers in. Okay. So R1 is 0, W is 0, EIJ is non-zero. What does xj have to be? It's got to be 0, right? Right? Because you got 0 over here and 0 over here. This quantity here has to be 0, but you're multiplying by a non-zero number. Right? Otherwise, this equation has no hope of being correct. Okay, so 0. Okay, so this, we can say the probability of R1 is 0 given that W is 0, just by looking at this, okay? It implies that it's the same as when the probability of xj is equal to 0. And the probability of xj being 0 is? The probability of xj being 0 is? No, not 0. It's a half. You flip a coin for each bit. Each bit is 0 or 1 with equal probability, right? So that's a half. That's pretty cool. Okay, what about the other case? Okay, so the probability, so we have to do this one up over here. So the probability that R1 is 0 given that W is not 0. Okay, so we have, so we have 0 here. We have W is not 0 here. What do these two things have to be in order for this equation to work? Good, yeah. So x is 1, and this entry here has got to be minus W. Okay? Otherwise, it's not going to work, right? Because this has got to be 0 or 1, and it can't be 0, otherwise this thing won't work. So it's got to be 1, and it's got to be times minus W. Okay, so this is equal to the probability that xj is 1, and E1j is equal to minus W. Now, I have no idea what the probability of E1j being minus W is, because I have no idea what W is or what any of the entries are in there, but I know what the probability of xj being equal to 1 is, so we can use the monotonicity rule and say this is less than the probability of xj being equal to 1, which is a half. Okay, so in one case, W is 0, in which case, in order for you to get unlucky, xj has got to be 0. In the other case, W is non-zero, in which case you have to be unlucky with it being xj being 0, and this other thing, but it's at worst a half. Cool? Okay, so in both cases it's less than or equal to a half. So just dragging this thing down here, and I'll continue on in black. Okay, so this means the probability of R1 equals 0 is less than or equal to a half times the probability of W being 0, plus the probability of, plus that's a half, less than or equal to a half, times the probability of W not being equal to 0. And we're in the exact same situation that we were with the 5 dice. We factor out the half, and it's either 0 or it's non-zero. This is a partition, so the probability of that is 1, so it's a half. Cool? I love those in so many ways. The beauty of okay, let's begin. All right, happy Friday, happy V-Day. Thanks for joining me, and